now, how do you find the useful? Right? Okay. It's a recursive algorithm, right? You start bottom up, actually. Well, who are the useful symbols? If you have a non-terminal that goes to sigma star, some expression sigma star, it's useful. Well, it's useful in one step. I can take it, substitute with sigma star in one step. So I look in my grammar, find the useful ones in one step. That's W1. These are the non-terminals that go to X, where X is in sigma star. They go to sigma star in one step. Find all of those symbols. That's set 1. Right? W2, set 2, will be all the symbols. What if I have a symbol and it goes to a combination of things in sigma star and symbols that go to sigma star in one step? If on the right side I only have sigma symbols, alphabet symbols, and non-terminals contained in that set, okay? Let's say here I have x1 goes to A and x2 goes to B. Okay? Here I have x1, x2. Well, he goes to sigma, terminal symbols, and symbols that can go to terminal symbols. So this guy will go to terminal symbols. Okay? In 2 steps, if you substitute them both at the same time. Okay? Get rid of this, substitute it. Get rid of this in the next step, substitute it. You get there in 2 steps. So in as many steps as non-terminals here, if those are useful, this guy will go in n steps. So he will be useful. That's W2. The right side has non-terminals in W1. Well, W3 will be all those symbols that go in expression whose right side contains alphabet symbols, and symbols in W1, which contain in W2, which contain W1. Okay, you found W3. Is this an infinite process? W4, W5. Are you guaranteed to terminate? Yes, because what are you doing here? You have a sequence of non-terminals. W1 is the set of symbols that go to sigma star in one step. W2 is a superset of this. It will be all those guys, plus the guys who go to them. So you add some more symbols. W3, you add some more symbols. But the set of symbols in the grammar is finite. A plus 1. When you found all the symbols that go to these guys, you don't have any more symbols. Then the process terminates. Those are the useful ones. So that's the algorithm. Okay, look at this set. I want to find the useful symbols. Okay, who is useful in one step? What's W1?
What?
F. Yeah. So how do you do that? You look on the right side of rules. And so what we're doing is we'll develop some algorithms to simplify grammars, and maybe some algorithms to reduce grammars. They're called canonical forms, like you did in databases, normal forms.
Yeah.
Okay. There is canonical forms. The idea is to reduce the grammar in a form that I can program very efficiently, so my parser will be faster. Okay, so let's talk about unreachable symbols. When is a symbol unreachable? Okay, everything starts with S. And the question is, which elements of sigma star can be derived from S? If, let's look at this grammar, for example. Okay? Look at the symbol D. If I start from S, and I start using substitution rules, will D ever appear Is it possible for D to appear in that derivation tree? No, you cannot get it from S. There's no way. Okay. Well, D is unreachable. So somebody is unreachable if starting a sequence of derivations, right, you can never get D in that expression. It's not possible. You cannot reach it from S. Suppose I have a symbol that is unreachable, and I have a rule that contains it. Do I need this rule? No. Are you ever going to apply this rule? No, because you will never be able to. Starting with S, you will never get D, so why you need this? The rule is useless and not applicable. So if you have a unreachable symbol on the left side, get rid of the whole rule. Okay. Now, if you have it on that side, how about that? Rule again, but do I need to specify this case? Or it's enough to say, oh, you have a rule, his left side is unreachable, get rid of it. That's enough. Why? Because if you have a rule, if this guy is unreachable, this guy better be unreachable, because if this guy was reachable, you can get to him, you can get to him. So it cannot happen that this guy is unreachable and this guy is reachable. It cannot happen. This means if that happens, I have to recheck my calculations. I made something wrong there when I was calculating who are the unreachable symbols. So this cannot happen. If this has an unreachable, this will be unreachable. So all I need to state in the algorithm is find all the unreachable ones, and then any rules you have whose left side is unreachable, get rid of them. Now the question though is, how do you find these unreachable symbols? The grammar will have hundreds of rules, right? It's complex. Okay. The unreachable is what is left after you found all the ones you can reach. So it's the same technique. So find the reachable ones. How do you find the reachable ones? Well, same algorithm, W1, W2. But now, W1 starts with what? The starting symbol. Whom can you reach from S? S. Then, in step 1, whom can you reach? Well, take all the S rules. S goes somewhere. And whatever symbols you have on this side, they're reachable from S in one step, in one rule application. So W1 will be all the symbols, this expressed mathematically. It's conceptually it's very simple. Okay? So all the symbols you can you have on the right side of the S rules, that's W1. You can reach those. So you can reach S, A. Okay. Now, in the next step, find all the symbols on the right side of rules whose left side is in W2. Like, whom can you reach from S and A right now? Right? Because A is reachable, so if I have a rule A goes, I can reach him too. So W2 is all the symbols, the non-terminals on the right side of the rule, whose left side is in W1. W3, all the symbols on the right side of the rule, whose left side is a non-terminal in W2. Will this process terminate? Sure, because at best you are adding new symbols every time. It's a finite number of symbols. It will not be anything true. So how do you find reachable? The same type of algorithm. Free language, and you take the transpose of it. Okay? It's also context free. What does it mean take the transpose or the inverse of it? The inverse of a language is the language that consists of all the strings where the inverse is of the strings in L. Like right? Is this context free? Sure, here is a PDA or here is a grammar. S goes to, give me a grammar for it. Who can give me a grammar for it? Right. S goes to A, S, B, or E. It depends what I told you N is. If N was bigger or equal to 0, A, S, B, or E. If N was bigger or equal to 1, I cannot say E because that will, or AB, replace ASB or AB. Yeah. Okay, this is context free. You just gave me a grammar for it. Okay. Well, is this context free? Of course. I mean, you just transpose the symbols, right? That's the inverse, the transpose. Ways to, there is a number of normal forms you can reduce a grammar to. The first example is called Chomsky's normal form. In this context, it's not conjunctive normal form, it's Chomsky's normal form. Okay, a context-free grammar is in Chomsky's normal form if every rule looks like that. Okay? Like what? Well, if every rule, it's, first of all, it's context-free, right? Which means on the left side, you must have exactly one non-terminal. I cannot change that. Context free. But instead of on the right side you could have anything you want, okay? Now we restrict it to either you have no non-terminals at all, you have alphabet symbols, right? And if you have only alphabet symbols, you're only allowed one. Like I cannot say A goes to ABA. No, it's not in Chomsky form. So either you have exactly one alphabet, or if you have non-terminals, you must have exactly two with no alphabet symbols in between. They are not allowed. Just exactly two non-terminals. If it's in this form, you call it, it's in Chomsky form. Right? This looks too restrictive, right? Oh my God, it doesn't look like that. It's too. It seems like it would be too limited in scope. How many grammars can be like that? Right? Well, actually, it turns out every context-free grammar can be reduced to one that is in Chomsky normal form. So there is actually an algorithm. You can take any context-free grammar, okay, and rewrite it to an equivalent grammar that is in Chomsky normal form. So it's not too restrictive. Now, why would we ever want to do that, to write in that form? One advantage of this grammar is the expression trees. They're binary. Two leaves at most, two leaves. We'll have one leaf, but then it terminates. It goes to the terminal and then it stops. It's binary. Now, what's the advantage of the grammar being binary? I can, you'll see, we'll use it in a proof later. Okay? When we're proving that things are not Turing computable and stuff and like that, sometimes you can use this idea, hey, yeah, it's convex free, there's a grammar for it. Okay, there is a Chomsky grammar for it. Okay, the trees are binary. Then based on that, we'll make some arguments to prove that, okay, something is computable. Okay. So how does this algorithm work? Let's do the algorithm, right? There are many steps in the algorithm. As a first step, I'll do what we just did. Well, if the grammar has unreachable and useless, get rid of them. I don't need to carry them around. Okay. So I'll assume you don't have any unreachable and useless. You already did that. Okay. So one is missing here. Okay. Number two, eliminate the empty rules. Well, when we said the form the grammar must have, we said if you go to a terminal, it must be exactly one, and it must not be the empty string. We had A in sigma, you know, it must be a real alphabet symbol. So if you have the only symbol that is allowed to go to the empty string is the starting symbol in a Chomsky form. Sometimes you have to allow S to go to empty. Because if S does not go to empty and nobody else goes to empty, empty will not be part of the language. There will be no way to derive empty. But some languages contain empty. Okay? So if I have to, because the language contains the empty string, I will make S go to empty. And that's the only thing I need to do. Nobody else will. So the question is, if somebody else goes to empty, what do you do with this? I want to convert it to a grammar without this rule. But I cannot just delete him, I have to do something. Right? So eliminate the empty rules. When you have non-terminals other than S going to empty, what do you do with these rules? What? So, what are this is a grammar. This is not a PDA. Okay, you have A equals empty. Say S goes to E, and then get rid of A equals to E. Okay, he has a proposal. Will this work? So you're saying, let's try something. Right? Just because some guy down there that is not S goes to E doesn't mean that E should be in the language. So automatically, as soon as you made S goes to E, you made E part of the language. That cannot be right. Right there, for that reason. Another reason is, even if E was part of the language, A goes to E, but also it might go to something else. So when instead you say this guy goes to E, now what do you do with him? He cannot, now he became useless. What is that? Yeah, useless. He became useless. So you destroy the grammar if you do that. Okay. So that will not quite work. I will need to know all the symbols that eventually go to it. Not you're trying in one step. Not only in one step, but I would like to know all the symbols that eventually can go to E. Let's find them if we can. Okay. So Yeah, so this is the algorithm. And it's similar to the W1, W2 for useless, and this is recursive algorithm. You know, expanding, it's not recursive, it's iteration. Right? I1, I2, out 3, I4, until you stop. It's a while loop, it's an iteration. So how do you find all the symbols that eventually go to it? Say, okay, let's find all the ones. W1 is the guys who directly go to it. Right? Lambda stands for either. So you find all the guys who go to it. W1. Now, what is W2? Everything that goes, it's all the guys who go to it so far, plus these other symbols that will go to a combination of symbols that you already know go to it. Okay? So everybody who goes to A, or a combination of A's, right? Yeah, let's not make it too complex because then you have too many rules. And I run out of room. All right, let's do this. Step 1, what do you find? What do I have to find? All the non-terminals that eventually can be reduced to the empty string. Okay. C. Okay, who else? C goes to E, right? Who else? B.
B.
Okay, who else?
J.
Yeah, but you have this A here. This can go to E, this can go to E, but A doesn't go to E, it goes to A. There is no way to make A down to E. So that's it, B and C, correct? In here, the right side, you only must have elements that go to E, otherwise you have okay? Then you'll be right. Okay, this is it. This is the set of symbols that eventually, through a sequence, can be reduced to E. B and C. Okay, now we go to the algorithm. Get rid of the empty rule, or rules. I will get rid of more than one. Okay, I'll get rid of him. But make these changes. What? For every rule, if on the right side you have any non-terminals that go to E, do I? No, leave him alone. No, leave him alone. Oh, yeah, B and C can go to E. So what do? You add some rules. All possible combinations of B and C being themselves or E. So this is being themselves, or B, start with one at a time, being E, and then two at a time, and then three at a time if you have more than three. So what if B was E? Then A can go to what? I said, this can go to E, this can go to E, all possible combinations, right? This is the combination that you leave that none of them goes to E. Okay, now, do one at a time going to E. So let's say B can go to E, then I'll get AC. C can go to E, AB. What else? Both of them can go to E. In which case A. So I have to add that. Going down here. Right? The next row. Okay. B goes to what? None of them go to E. Right? Only this guy goes to E. Then I have BCA. Or only this guy goes to E. I got BCA, same thing. Only this goes to E. I got BBA. Right? Now, two at a time going to E. What? No, two at a time. I'll do three at a time and then. Yeah, if all three went to E, I get small a, right? Okay, but let's do two at a time and then three at a time. Okay, two at a time. CA. Or it could be those two. BA. Or it could be those two. But that's BA. What? Or if three go to A, then as you said A. That's it. Add all those rules. Okay. Then what else? Now B goes to C. What? Wait, not yet. B, I'm applying my algorithm. Okay. I'm a blind person. An algorithm is a blind process. It's just what they told you to do. You're thinking as a human, okay? So B goes to C. Well, C can go to E, right? Okay, then B can go to E. But now I introduced another. Who was going? This guy was going. Now I got an empty rule over there. Right? I got rid of C goes to E, but I got B goes to E. Well, get rid of B goes to E. Well, I'll get rid of it. And wherever, I have B, I'll make it go to E. Okay? But I already did that. AC, right? AB. I already did that. That's part of the process. So I don't need to add B